Hello and welcome to chapter 21. So now we continue on with our study of the planets. So we've already studied Earth. Now we're moving on to Venus and Mars. So these are still the terrestrial planets. So our learning goals are summarized right here, and all of these questions you should be able to answer by the time you finish the lecture. So Venus is often referred to as the Earth's twin. So it's and that's mainly because it's similar in size, mass, density, and composition. So a whole lot of similarities there. One example is just a similar in size. Just to note that point there. The diameter of the Earth is 7,917 miles. So if we just put that here, diameter of the Earth is 7,915.5. That should be a decimal there. Miles. And Venus is 95%. Its diameter. So this is the diameter right there. So the diameter of Venus is 95% of the diameter of the Earth. So if we just multiply that out, we get 7,521.625 miles. So change the color of my pen. So that means, if we have the diameter of Venus right here, if we have the diameter of Venus right there, Earth's diameter is just slightly larger. So just a little bit larger, not that much of a difference. 95% there. Obviously 100 if the diameter of Venus or diameter of Earth is 100%, 95% of that, we see just not that much of a difference between the two. So if you stuck Venus right in front of the Earth, it would sort of look like an eclipse of the sun. You would just see a little bit of the Earth around the outer part of it. It would not be a total eclipse. You would just see Venus sitting right over top of the Earth. So that's similarity in size, and then their density, their mass, is also relatively the same. Very similar mass and density, as well as the composition. And the reason for their similarity in mass, density, and composition is recall how planets, in order to understand this part, recall how planets are formed. So we want to remember that the sun was forming here, and when the sun was forming, it had all that solar nebula all around it. And in those rings, in that nebula, we had Mercury, Venus, Earth, Mars, Jupiter, Saturn, on out, the further away they went. But so Mercury was formed the closest to the sun, and Venus and Earth were pretty much formed right in that same solar nebula. Maybe not exactly in the same ring, but in that same area. So because they formed so close to one another, their composition is going to be relatively the same. They were stealing material from each other or grabbing at the material closest to each in order to grow and form. So that means since they were built out of the same sandbox, basically, they're going to have very similar mass, density, and composition. The only differences are that Venus is a very dry, hot surface. So these are Venus's characteristics right here. So Venus is a very, very dry, hot surface. We know that the Earth is a very moderate in temperature. We have a lot of temperature differences, cold, hot, and somewhere in between. But our hot is not hot enough to suffocate us or burn us. I mean, obviously we get sunburn, but we don't die from it unless it was an extreme exposure to the sun, and that's rare for that to happen. But on Venus, it's so hot that a human being cannot survive on it. So the Earth's temperature is pretty moderate compared to Venus, and then Venus is very dry. But Earth, obviously, we get rain and snow, and and we have oceans and lakes, and we get a lot of water on our surface. So again, comparatively speaking, Venus is very dry and hot compared to the Earth. Venus is also 100 times more dense of an atmosphere. So here, if I erase my little Earth picture around here, so the solid part right there, this is showing the physical planet right there that with this part right here is so the part we're looking at with the diameter here. That's the part you could touch, but again, remember the atmosphere surrounds that ball. So the atmosphere of Venus is 100% more dense than Earth's atmosphere, and so that density of its atmosphere means that this surface, we're looking at the surface in this picture here, but it really means the dense atmosphere means that surface is completely hidden all the time by a very thick clouds that completely envelop the planet. So the planet's pretty much wrapped in this cloud, a very dense cloud cover. It wasn't until very recently, pretty much I think as early as or as recent as the 1960s, that astronomers were able to actually see through those dense clouds and look at the surface of Venus. So a lot of those we'll look at a lot of those NASA missions that discovered or were able to chart the surface of Venus, that peer through those clouds. So a lot of high-tech gadgets or high-tech telescopes and sensors and probes were deployed in order to understand what the surface of Venus is and to be able to see through those clouds as well as characterize those clouds. A little more specific about those tools. Most of the tools that the astronomers were using were actually microwave technology, and astronomers were actually able to measure the black body emissions in the microwave spectrum that were emanating from Venus in order to be able to determine the surface temperature. And then they used radar technology to actually penetrate the clouds and then be able to see through or penetrate the clouds in order to study the surface of Venus. And then about approximately 25 spacecraft from NASA have either flown past or orbited Venus and collected that imagery as well as probing that atmosphere. So the resulting pictures of Venus that came away from these missions reveal a vastly different view of what Venus looks like. We now see through that thick cloud. So instead of a fluffy cotton ball look, we end up getting the yellowish image that we see right here, that we see in this picture actually. So Venus's rotation's a little odd. It rotates once every 243 Earth days. So remember that rotating is rotating, that it means that the planet's rotating about its own axis. Revolving is, or revolution, is when the planet revolves around the sun. So that rotation, let's just look at that rotation a little bit more. So here's its axis, and if this is the north, and you're looking down on it, so you're looking down at the North Pole, you're above it up here. We'll draw your eyes right there, and you're looking at Venus from the perspective of being north of the planet. So when you look at it from that perspective, and if you look at all the planets from that perspective, almost all of the planets rotate counterclockwise. So that means they're rotating this way. So remember, clockwise would be that way. This would be clockwise. and this is counterclockwise. So I said almost all of the planets. Well, Uranus and Venus are the two exceptions. So Uranus and Venus rotate this clockwise way. So here's their axis, their northern axis, and they're rotating clockwise. They rotate clockwise around their axis. And then during the Doppler shifts of a radar pulse reflecting off of that, or reflecting off of the planet, that's how it's figured out that they rotate, that Venus rotates once every 243 Earth days. So that's a pretty slow rotation. So just a note here, retrograde, we're saying that Venus rotates once every 243 Earth days, and retrograde to most of the to almost all the other planets. So the retrograde means that it's rotating either backwards or in the opposite direction. So like we mentioned, all the planets rotate counterclockwise except Venus and Uranus. So those two planets these two planets rotate clockwise. The rest rotate counterclockwise. So these two planets rotate retrograde to the Earth. And so to try to understand why it rotates so slowly, most people just thought it was that the planets were stuck in a different track, a different rotational posture or position, and that's kind of likely, but really. So really the explanation for why it rotates slowly and backwards is that a possible cause. So it's not a definitive answer. Astronomers are still trying to understand this. But a possible cause is that the terrestrial planets, they are the ones that are closest to the sun. So that's the first three, and then the moon too. But it's also believed that they have the molten core, that real hot, dense core, and as well as the dense atmosphere. And under those conditions, these types of planets can be their rotation can be gradually reversed by solar tides in the atmosphere. So the planet could have been rotating this way, and then solar tides slowly stopped it and unwound it, or made it start going in the opposite direction. So that's still a hypothesis, though. It's possible that played a role, but it's not a definitive answer yet. So Venus's interior is the uncompressed density is slightly less dense than the Earth's. The density and size of Venus indicate that one would expect Venus to have a very dense metallic interior, just like the Earth, that molten core. But Venus does not have any detectable magnetic field, and that's a mystery. If Venus really does have a dense metallic interior, it should have a magnetic field, just like the Earth does. So because the density and size of Venus is so similar to the Earth's, it would indicate that Venus has a metallic interior, a very dense one. But why there's no metallic field with it is still a mystery. It's a possibility that the core is a solid, as opposed to that molten liquidy lava type interior. It could be very possible that it's solidified, and that would change, or that would explain why there's no metallic field from Venus, whereas with the Earth's core hasn't solidified. It's still that molten lava type, and consequently it's in flux or flowing, and that would generate or provide that magnetic field. So Venus's atmosphere, even though it's very dense, and there's so many other similarities between Venus and Earth, the atmosphere is the biggest difference. So Venus's atmosphere is completely different than Earth's atmosphere, very unlike Earth's atmosphere. So Venus's atmosphere is mostly CO2. and it's also very acidic. It's so dense that humans can't survive. They would crush under the pressure. And then there's also multiple layers. So what that means here is that we have the planet right here, and then a layer of atmosphere, and more like an onion ring. So if you're looking at it this way, you got to peel through this layer of an atmosphere. You get some space there, and then you got another atmosphere, another layer, peel through, and you get a little bit more of a layer. So another way to look at it, perhaps a better way to look at it, is right here, this picture from your textbook. So you see these when you're down. You see the Earth's atmosphere very much here, and Venus is off the charts, way over on this side here. But you see at an altitude of 50 kilometers, you see a haze here, and then you see all these dense clouds right in here. And then out here at 100 kilometers of view, you see a different type of haze forming. And temperature-wise, here you're going to get a little bit a colder temperature on that part. This area here is colder. It's in the negatives. But when you look out here, let me erase my own drawing here. But when you look right there, right at that part, you see where the red, see this bulb right there, the thermometer, that ends right there. And that brings us up to 200 degrees Fahrenheit. So the outer haze, this outer part of the haze right there, the first layer right there, if we were observing from Earth right here, that first part, this haze right there, is very hot. It's 200 degrees Fahrenheit. So we human beings can't survive in 200 degree Fahrenheit very long. Our body is mostly fluid, and that fluid would burn off. We wouldn't survive. We would dehydrate and lead to death. And then once you work your way through the clouds here, and you get to this inner haze or inner atmosphere, that would be the inner ring. Now you're freezing. You're sub-zero. You're down to like sub-zero temperatures. And if we see again, right where that thermometer ends right here. So we're going to put that at roughly about negative 100 degrees. So that, again, is too cold. And a human being with mostly water body composition would freeze, literally freeze to death in that type of an environment. So Venus, because it has so many layers of an atmosphere, it's considered a runaway greenhouse where CO2, a carbon dioxide atmosphere, is very opaque. It's very opaque to the infrared radiation, and the surface temperatures are hot enough to melt lead. So 200 degrees Fahrenheit, you can melt lead on that. It's very opaque to infrared radiation, but then high winds in the greenhouse effect carry heat uniformly around the planet. So if we drew our little planet right here, you pretty much have that greenhouse effect again, the runaway greenhouse gas. So very dense here atmosphere again. So if we compare to the Earth, our greenhouse effect, we're getting warmer temperatures in here, but obviously nowhere near the point here where you can't melt lead on Earth by just naturally melt it. We have to heat it up. We have to heat it up, but the Earth's atmosphere itself cannot melt the lead. And so the warmer and warmer our atmosphere gets, of course, the temperatures go up. Well, Venus is already there. Its greenhouse effect is so strong compared to ours that the effect makes it so hot on that interior and hot enough again to melt lead. And the swirling high winds, the high winds swirl pretty uniformly around the planet. So if we think of Earth, if you're let me draw a little bit bigger of a picture here for this purpose. So if you're on Earth, and here's USA over here, and let's just go to the other side of the planet. I forget. Let's just let's put Asia over here. So a high wind carrying high winds carry heat uniformly around the planet. So uniformly around the planet, that means it's just as windy in Asia as it is over here in the USA. So that wind just travels all around all the time, and it keeps that heat pretty uniform around the planet. And that's what's happening on Venus. So in America, we know that that's not true. You can just go from Chicago to Florida and see that the wind is not the same on in both states, and that's just right over here in the USA. But the rest of the planet too does not experience a uniform high wind or uniform heating. Venus, on the other hand, does. So no matter where you are on Venus, you're going to get that same high wind and uniform heat. And then consequently, Venus, the greenhouse effect, Venus, no water, there's no water on the planet to absorb that carbon dioxide. So that CO2 emissions that we are so worried about on Earth, the Venus environment or greenhouse is pretty much all carbon dioxide. It's just trapped in that atmosphere, and the atmosphere of Venus is so dense that those CO2 molecules cannot escape. The CO2 molecules cannot escape the Venetian atmosphere. So all the NASA missions that explored Venus's surface, radar imagery is pretty much the technology responsible for revealing the Venetians. So again, early radar images are responsible for revealing the Venetian surface, and that technology revealed that there are definitely mountains on the surface of Venus, as well as plains and craters as well. So a little bit, you can see a little bit here of here you can see a horizon on Venus over here, and then this is a little bit of the instrumentation that was ejected once the spacecraft landed on Venus, and then here's the edge of it. But then you can also kind of see mountainous terrain right there, and that would be indicative of probably a crater right over here, a little bit more high range, a little more range right here. So again, you can see. Not a smooth surface is really the point we're trying to make here, is that early radar images showed that Venus does not have a smooth surface. There are parts of it, there are parts of the surface that would be plains, but then Venus also has mountains and craters. So the Magellan spacecraft was a NASA effort, and that spacecraft characterized the surface of Venus pretty well. So I'm sorry, I forgot to mention in the last image, so the one right over here, this image here, that actually was from the Venera 13 lander from NASA. And that spacecraft explored Venus in 1982, and it carried this little, the instrumentation right here that we're talking about is actually a camera that was ejected and meant to land. It wasn't really debris. We shouldn't think of it like that. But it was a little camera that swiveled back and forth. So when that camera rotated, if you just think of it rotating from left to right or swiveling from left to right, every time it swiveled from side to side, it collected a photograph or took a photograph of the surface. And this funny looking yellowy glow up here, that's produced by the actual atmosphere as detected by the white light of the camera. And then removing that haze off of it, we can see the rocks and or mountainous type terrain. This is more rocky, but it's a little hard to tell how high it would be. And then later came the Magellan spacecraft. So this imagery, or this image of Venus, again, is from the Magellan spacecraft. And Magellan, that was a joint venture between the U.S. and the Soviets. And that was a mission flown in the late 1970s. And it was a radar device. Magellan used radar technology to probe through the atmosphere and explore the surface. And we see two little landmarks on the surface right here, and it's just these two, right? This one right here, and you can see a little better here, and then this one. So they were trying to figure out, or the astronomers noted those to try to figure out if that was a water avenue, or maybe some type of flow of or like our oceans, rivers, lakes, tributaries. If it was the same kind of setup there. So the maps don't really show how. So what the scientists ended up coming back with, though, when they took these images, is obviously a radar image, but the orange color here, that does not mean that Venus is orange. Only Mars has a definitive natural color to it, the reddishness, and we'll study that in a little bit. But I don't want you, the student, to think that the picture right here it shows Venus as an orange, yellow with yellowy types of atmosphere or yellowish lines there. The color is actually when the image comes back, whether it's infrared or microwave or even a CAT scan, if you've ever had a CAT scan yourself, one without contrast. When you get the CAT scan, it comes back gray. It's pretty much like a grayish image with a little bit of gradients in there that look maybe kind of whitish at times. But pretty much what the image is that you see is predominantly gray or some gradient of gray. You might have really dark gray, a little bit of light gray, and various shades of gray in between. But that doesn't really tell you much. It's hard to look at an image like that. So that's often why a doctor will tell you to get a CAT scan or an MRI with the contrast. So the contrast provides color, and it provides color based on temperature. So maybe so if you're getting a CAT scan of your brain, the areas of your brain with a whole lot of activity would show up as red, and areas where that are maybe at rest would be blue with less activity. Similarly, the similar line of thought is with a PET scan with cancer, and when the dye or the contrast is injected into the person, the area of high activity would show up as red. So cancer is very prolific, and the cancer cells are constantly multiplying, dividing, growing. And so that tumor growth shows up as red, and everything else would show up as blue or green or yellow, like a cooler colors. So the similar type thing here with the planets. When the astronomers collect an image, the image comes back as gray and a variety of shades of gray. But to really analyze it better, the scientists usually have to choose some kind of a color or all colors, but they would have to specify. If you choose all the different colors, like if you think of the rainbow, and you have red, green, blue, yellow, violet, I forget all the colors in there, but you would have to say this means cold, this is going to be defined as hot, this is going to be cold, and then green somewhere in neutral maybe, and then this would be or blue and violet also somewhere in there, where the blue would be the extreme cold. Maybe we would assign that negative 100 degrees, and red would be 200 degrees. And in doing that here with Venus, orange was what would, instead of choosing red, the astronomers for the Mercury or the Magellan mission chose orange as the hottest of temperatures. So that would be your 200 degrees Fahrenheit. And then yellow in there is cooler. So yellow might have been 100 degrees Fahrenheit. So the temperature variations that were collected by the Magellan radar technology showed temperature differences in a few areas, and the color yellow and orange highlight those differences in temperature. And then you could see a few areas that were black right here, these areas right here where there's no temperature there. So either they couldn't collect the data there, or for some reason or other, there was an area, even though the winds surrounding Venus keep a uniform temperature, it's uniform actually in the terms here, could be an approximate range of very close temperatures. So it might be a range between maybe 180 to 200 degrees Fahrenheit, with the hottest parts right in here being 200, and then you get a little bit of a change, a little bit of a differential. So the radar maps don't really show how the surface would look to the human eye, but rather they provide information about actually in the case of Venus, not a temperature differential. Temperature actually is uniform, so it's going to be a little closer than a 20-degree gap, but really it's going to show differences in altitude, roughness, and in some cases chemical composition. So if you transmit a radio signal down through the clouds and measure the time until you hear the ping back or the return, then you can measure the altitude of the surface. So as a result, part of the Magellan data gives you an altitude map, and then you could also get the surface temperature map as well. And then the Magellan spacecraft also revealed that much of the surface of Venus is lava flow, and but that doesn't look very bright under a radar map. And same thing with uneven terrain or like pretty smooth terrain, doesn't show up all that well. But again, the Magellan view helped to really, or Magellan spacecraft really helped to characterize what the surface of Venus actually looks like. So we talked about hypotheses and data accuracy in the beginning of the semester. But a little clarification here is that when scientists add color, just like when a doctor adds color or contrast to a CAT scan or MRI, they're not altering the data. So one could call it manipulation, meaning that your raw image is enhanced. You're adding color to it. And it makes it easier to detect a tumor, or in the case of astronomy, it's making it easier to detect variations in the surface or variations in the temperature. So variations in the surface would be mountains versus craters versus a plain, or in the case of temperature, you're looking at temperature differences. So you're not changing the data. You're just displaying it or in a different way. Instead of displaying it as a black and white image, you're displaying it as orange and yellow. And the orange and yellow help you more easily distinguish where there's higher surfaces. So it could give you a more, it could provide finer details to your study. It doesn't, when we go back to this picture, one could arguably say, well, who cares if it's black and white versus yellow and orange? It's yellow and orange doesn't make it abundantly obvious to us, at least looking in this picture, that there's various differences in the surface. But to the astronomer that's a little more trained in looking at the differences, when we pointed out these two areas right here, well, the astronomers were able to say that the image that these are actually volcanic images. So it shows a lot of scattered impact craters, and the volcanic eruptions or the volcanoes spewed out a lot of matter that caused or created all the different craters on the planet. So in this image here, the impact craters and the volcanic regions, and these two are volcanic regions. So we can see the highlands right there, and then the lowlands. So this would be a crater. That would be a crater here, and then this would be the volcano, the much higher one. And it's also the higher temperature. Bright white would usually indicate the extremely high temperature in comparison to the cooler surroundings. So that's really the difference in these color contrasts. It helps you to see a little better what is volcanic or what is mountainous versus what a plain would be or a crater. So again, they're not changing the data. The data remains the same. They're just using color enhancement or color technology to provide a finer level of detail in the imagery. So another type of map, again, is an infrared type map. And here's where you put, much like the MRI, where you put all those different colors in there. So the top of the volcano is coated with a mineral, and it's not a very stable mineral or stable coating. On the warmer lower slope area, you see a whole lot of color. So you see a lot of different variations. So if you just trace to this part right there. So this is our call out block, and we're calling attention to the green, and you see right there the yellow and the red, and especially the scattered yellow all around here shows you a very unstable slope where a lot of temperature change is occurring. And then the old lava plains in this region of Venus are smooth and marked by two large volcanic calderas. So that's the cauldron. That's basically what we would look at is this is the volcano, and out of the volcano comes the lava. So they're the cauldrons that they're talking about here. And then the craters, there's about 1,000 impact craters on the surface of Venus, and they're pretty uniformly scattered over the surface, and they look real sharp and fresh or new due to the lack of water erosion. So in this image right here, again, it's a radar map, and you could still see this if it were black and white, but I guess it just looks a little more pleasing to the eye to use the orange and various gradations of orange. So you see a volcano here, another one here, another one here, and if we had a larger image, we'd see quite a few because they're uniformly scattered there. But when we say they're sharp and fresh, it looks like a volcano that just erupted. So it looks like it has lava all stuck in here and maybe smoke coming out of it. And that's just really because there's no water on Venus. So the water is not eroding away the surface. Whereas if you look at a volcano in Hawaii, you can actually grade it or age it much like you would a tree. So you could take that age right down to this part. But when it erupts, even if it erupts maybe every 100 years, there's still rain in Florida, in Hawaii on a daily or monthly basis. You have rain totals, and that rain is eroding away and eroding away. So when the lava flows out of it on Earth, lava comes out of it on Earth and flows down. There's going to be a lot of ash and a lot of debris, and then it rains and washes away a lot of it. And the more it rains, or over time, eventually all that erodes away. But on Venus, you're not going to get that erosion. So it always looks like the volcanoes just erupted. So volcanoes dominate the surface of Venus, and lava flows cover most of that surface. So again, we're looking at a radar map here, and here's the lava flows. This is where the lava's flowing, and here's the right where that little spot in the center is where the lava comes out of, and this is an artistic or a simulated image, an artist rendering basically, and you see here's the core, the centers of the volcanoes, and then all the lava coming out of it, and then you can see that mountainous or volcanic layering all around the planet. So on Earth, there's two types of volcanoes: composite and shield volcanoes. And chains of composite volcanoes, though, are actually not found on Venus or on Mars. And that's evidence that subduction and plate motion does not occur on those worlds. So on Earth, when you get these plates coming, when you get the plates crashing into each other, one of them goes, one of those plates subducts or goes underneath the other plate. So here's the subduced plate, is this one right here. That's the subduced plate. And those plates pull apart and cause an earthquake, or they collide into each other and they push that rock up and they create mountains and volcanoes. And shield volcanoes all shield volcanoes are produced by hotspot volcanism. So hotspot volcanism means the volcanoes are active, and you're gonna, if you look deep within within the volcano, if you're looking down from where the eruption comes out of, so you're looking into or inside the volcano, you can see a lot of columns or a whole lot of magma rising from deep within the mantle, and they're generally not near the edges of the plates. They're pretty much like that bubbling cauldron that you would expect to see. So that's the hotspot volcanism. They got a lot of hot activity going in there, like they're getting ready to erupt, and they grow very large because of repeated eruptions that are happening in the exact same place in the crust. So back to Venus, our volcanic activity. You can see the imagery here showing it. Now here's your black and white imagery. So all these little lines right there, it's really hard to tell what they are or how many. They kind of blend in. So that's why you want orange and then a whole lot of grades of orange to highlight all those little spidery looking veins. Basically, you want to highlight them, you see them better. Same thing here. You see all the lava running down, but you really can't see the actual opening or the hole. But if you look at it from a different perspective, here we're kind of looking at it head on or top down, like we're looking right into the volcano now. And when you see that, you see these little flattened areas, like little volcano domes. They're pushed down, or smaller volcanoes. But then you see a lot of that activity, a lot of the rings of lava flowing away. And then in this area right here, you have a much smoother flow, or I guess a blanket of the lava would be a better way to explain that. So how Venus actually formed. The textbook has that we're really unsure how it formed. And then differentiated and evolved. And the reason that they're of the uncertainty is just because it's Venus is unlike the other terrestrial planets. Again, it rotates in the opposite direction. It's much denser, much hotter. The thought is that there once was water on the surface, but that it evaporated because of the extreme carbon dioxide levels, that high greenhouse effect. Its low density crust is probably more buoyant than Earth's, and that means it resists being pushed into the interior. So it's kind of bouncing along or floating along pretty good on the onto the mantle. The crust is not rigid enough on Venus for that plate activity. Even if there were plate activity, it wouldn't. It's not going to cause the earthquakes that we see on Earth, and on Venus you won't see them. And then the atmosphere of planet rids the interior heat, or rides the interior heat through large convection currents of hot magma beneath the surface, and that again bubbles up and spills over. But back to the uncertainty about how Venus formed. We do know, like we studied earlier again, that here's the sun. And the sun had that those gas rings around it, and Venus and Earth formed out of it. But how it changed, or how it differentiated from the Earth. Why isn't it exactly like Earth? Since they both form so close to the sun, and in that nebula, the same nebula, why did it turn out different than Earth did? It's so close to Earth. It's the planet closest to the Earth. So why isn't it an exact twin? We would expect it to be an identical twin in this case. But the reason that it's not an identical twin, that's what astronomers are still trying to figure out. Why Venus differentiated and evolved differently than the Earth. So now on to studying Mars. So Mars is intermediate in size, and it's about half the Earth's diameter. So Earth is much bigger, and then half that diameter is the size of Mars. Mars rotating on its axis, if we drew the axis right down the center, it's actually tilted. Mars is actually tilted, its axis is tilted against the orbital plane by about 25 degrees. So if we call this the orbital plane right here, it actually is tilted by a degree of 25.2 against that plane. So the image here shows it not tilted, but it actually is observed by astronomers and measured to be a tilt of 25.2 degrees. Mars has seasons, and those seasons are very similar to the seasons on Earth. So that means Mars, these little ice caps here, Mars experiences growth and shrinking of their ice caps and in a changing environment, much like the Earth does. So the interior of Mars, and now this is not the interior of the atmosphere, it's literally the interior of the planet. And similar to Venus, there's no overall magnetic field. So that's different than the Earth. The Earth does have a magnetic field, but Mars does not have an overall magnetic field. There's a few traces of magnetism frozen into some of the sections of the very old crust that hasn't melted away yet. But again, there's no overall magnetic field, no active magnetic field, certainly no active one. The tides on Mars are less than 1 centimeter high, so you don't get big tidal waves that you get on Earth. And Mars has a very dense core, but then a less dense mantle and a very low density crust. So again, let's refresh our memory here. So we have the core, and then we have the mantle, and then we have the crust. So they're the three layers of the solid object and or of the planet. And Mars's interior lost its heat very rapidly, and the core froze solid. So when that happened, it lost that dynamic effect, or the dynamo effect of being able to sustain all those different seasons the way Earth does, and also to be able to sustain life, habitable life on the planet. So Mars's atmosphere, very similar to Venus, 95% CO2, but it also has nitrogen and argon in the atmosphere. So Mars's atmospheric density at the surface is only 1% that of Earth. So because the atmosphere is 1% that of the Earth's atmosphere, much more minerals or much more atoms escape the Martian atmosphere than do escape the Earth atmosphere. So Earth has the greenhouse effect, the CO2 is trapped in there, but oxygen is also a part of our atmosphere, whereas on Mars and Venus, oxygen escapes the atmosphere. So you wind up with primarily CO2, and then in Mars, nitrogen and argon. So water vapor, or water can only exist as ice or vapor on Mars. It can't exist as a fluid. So you go from one extreme to the other on Mars. You have it as ice or it vaporizes. You can't sustain anything in between like you can on Earth. So the redness now here, this is a true visual. This is not a color enhancement or anything like that. So Mars definitely is red, and that red color is caused by oxides that are trapped in the soil. So these oxides that are trapped in the soil on Mars, it's actually large reservoirs of carbon dioxide that got trapped in the soil, and that pretty much accounts for the reddish, the red color, and as well as the gradients where you see the black here. That would be no oxide, no carbon dioxide. But we also said that there's a little bit of couple of other elements on the Martian planet, nitrogen being one of them. So nitrogen, nitric oxides would also be found in the soil here. This picture, was taken by the camera on the Curiosity rover. So the rover that landed, so NASA, NASA's mission that landed the Curiosity rover. The name of the rover was Curiosity. That camera collected the imagery here, and that camera, the rover, actually landed inside Mount Sharp. And that Mount Sharp is located inside the Gale crater on the surface of Mars. And then there's been a lot of missions that orbited or flown by Mars, but the ones that landed on the surface of Mars collected a lot of the rocks and soil samples and everything like that. So all those different things that were picked up from the landers. Obviously, no person has set foot on Mars, but these landers, these Martian landers, probe the soil and collect samples, and then that's actually flown back to Earth for evaluation. So volcanic activity has also been noticed on Mars. But we'll get to that. Looking back at the Martian atmosphere again, Mars has lost all the lighter gases. So those light gases, the smaller gases, are able to move fast enough that they can escape the atmosphere. So they get a velocity known as the escape velocity, and that means that that particular velocity is fast enough to allow the molecule or help the molecule escape the atmosphere of Mars. So Mars has polar ice caps, and that's what we're looking at right here, the polar ice cap right here. And then an artistic rendition, we see the ice all around here. And then the active volcano. So Mars's surface, Mars has seasons, so consequently they have changing weather. Mars also has a very complex geology, and there are signs on Mars that water at one time flowed on the surface. So you can see on Mars, you can see a lot of erosion. And here's all the different missions. Again, here's the Viking mission to Mars, and Spirit, and here's Curiosity, where that landed. And then a lot of flybys would have caught that they have a South Pole and a North Pole. And then the cooler temperature up here could indicate that that's where, along with ice, along with the fact that ice exists there, the cooler temperatures lead one to conclude that water at one point flowed on the surface and just froze over, or in some cases down here may have evaporated in these regions, but it accounts for the cooler temperatures. So there are volcanoes on Mars, and they're shield volcanoes, and they have very shallow slopes. So the shield volcanoes have that molten lava, or the active lava going on, like the bubbling cauldron of lava. When you look through the whole way down into the volcano, you'll see a lot of activity there. The Olympus Mons is the largest of the volcanoes in the entire solar system. So Mars has the actual largest volcano. So after that heavy bombardment era during the planet formation, a lot of canyons and volcanoes had formed on Mars. So the Valles Marineris is a network of canyons about 4,000 kilometers long, so a network of canyons. And it was produced by fault lines that allowed blocks of the crust to actually sink. And then they enlarged it. They were enlarged and modified by further landslides and erosions. And then Tharsis is a gigantic volcanic bulge on the crust of Mars, and magma rises from below the surface and is pushed up and has consequently pushed up the crust and broke through it. So when you have the remember you have the crust there, and then here you get the crust pushing through. So instead of that nice neat little round ball, you wind up with a volcano on the surface there. So the magma rising from below was pushing up, and it pushed up on the crust and eventually broke through, creating that volcano. And it repeatedly breaks through to keep that volcano or giant bulge active on the surface. So looking for water on Mars, you're looking for these little divots or craters would indicate maybe that it was a little pool or lake or ocean, something of that sort. These look like teardrops, but they're actually not. So it's just like a smoother surface. Might be an ice cap, but they're still trying to figure all that out. So some regions on Mars appear to have collapsed because of the withdrawal or the evaporation of water below the surface. And then other areas, right, like the second part right here, have splash craters, and that suggests, like if you see some water spilling over, that the water was present within the crust and maybe rising above or pushing up the crust. And then gullies appear, a big gully right there, in steep slopes, and that's typical of water flowing. So when you look at a mountain range and you see a little bit of trickle of the water trickling down or coming out, that would be what this indication here. And then this groove, a really big groove like that, would be a channel or an indentation basically, and it would be long-term flowing of water. So the longer the water flows, the more it cuts away at the surface or erodes. So if you have a mountain on the Earth's atmosphere and you have a little stream trickling down, that stream erodes away at the rock of the mountain, and it creates that big divot or indentation there, or in this case what's being called a channel. And then a few other here again is another type of picture where it shows that possibly here was a flowing stream. Could have been. It's dried up now. And then these could have been leftover remnants of water, or maybe this was the pool of water right out here. So these images help astronomers to try to figure out what was going on. So this is actually a visual, and then here's a radar map, and this would indicate the South Pole, or an ice cap on the pole. And astronomers pretty much think that there is actually water on Mars. They just haven't found it yet, and it's just hidden. So maybe it's hidden here. Maybe this is one area where you got it hidden underneath the surface. Or maybe it's under the surface here waiting to bubble up again. So it's just a matter of finding exactly where it's trapped. The existence of the ice caps indicates that there could still be water beneath those ice caps, buried farther within the crust. So Mars has 3 periods of development. The Noachian period was the heavy bombardment area or period of planet formation, And so during that period for Mars, the plains were flooded by lava flows, and liquid surface water could have been present at the time, um, and created those channels that we just saw in the other pictures. And then the Hesperian period of Martian development is when part of the surface was covered by lava flows, and the outflow of channels may have formed at that during that period. And then the Amazonian period is the uneventful, slow evolution that leads to what we know of Mars today, or what we can observe of it. Mars also has moons, two of them, Phobos and Deimos. And Phobos is marked by the large crater, and then Deimos, it looks much smoother, and it has that really weird shape to it too. So it's not completely round like our moon. It's kind of got that weird shape there. Looks like it has a little tail or something folding up in it. So these moons, the way they evolved, their properties suggest that they are actually asteroids that Mars was able to pull into its orbit. And the moons are very dark, low density objects. And but how, like, if the hypothesis is correct that these were actually asteroids, how did Mars actually capture them and keep them in their orbit? It's not that easy to do, and it's not common. It could have happened, but understanding whether or not it did or and how is what astronomers are working on now. They're too small. The moons are too small to pull themselves into a spherical shape, so consequently, you get the really weird shape of that we saw in the pictures earlier. Both of the moons are heavily cratered, and Phobos has parallel grooves in it that's not seen on Deimos. So that's everything for this chapter. And if you have any questions, please feel free to contact me.